Hello, my name is Grace McFassel, and today I'll be talking about how to obtain every action-based sensor. How much does a robot need to sense? This is both a theoretical question and a practical one. Consider a simple problem such as this robot that needs to move from its current location to a goal. What information must it sense to do so? Understanding those requirements can yield insight into the problem structure or the functionality of the robot itself. Practically speaking, we'd often like to balance our temptation to give robots the best sensors we can with the much more pressing concerns of cost and feasibility. In this case, a GPS system and a lighthouse are both capable of guiding robots with different sensing systems towards the goal. However, a lighthouse may be much cheaper and simpler to implement than satellite communication. No matter if we are concerned with theory or practice, understanding the baseline that all other sensors must be as good as is valuable. Previous work in this area goes back to a classic paper by Erdmann, which developed the concept of action-based sensors. These abstract sensors do not give observations to the robot, but instead prescribe actions to lead it towards a goal. In this case, the minimal sensing requirement is the ability to distinguish regions that require different actions to make progress. All the robot needs to know is just enough such that it knows what to do next. In order to know what the robot should do next, we turn to plans. Action-based sensors and plans are closely linked. Solving planning problems depends on the sensors we have, and the actions returned from the action-based sensors depend on the plans from which they were defined. Originally, when defining an action-based sensor, it is derived via backchaining from the goal. This gives us actions that correspond to the fastest solution and to a certain plan. We can then break up the world into regions based on the actions that make progress there. This construction, however, does not always play nicely with our constraints. Perhaps our robot lives in a world such as this one. Windows create varying light levels while a landmark is only visible from a few areas. Perhaps this is all our robot can sense about the world, and we wish to reach a goal no matter where we start. Unfortunately for our poor robot, regions C and D are indistinguishable. Both have the same lighting levels and a visible landmark. This is a problem, as our action-based sensor created through backchaining requires us to be able to distinguish C and D from each other. The action-based sensor prescribes actions and regions for the fastest solution, but fails to be useful to us in the face of other constraints. Despite this, there are clearly plans we can design for this robot that will let it reach a goal from any starting position in the world. Not only do there exist plans that can solve this planning problem, but we can derive our own action-based sensors for them through grouping together regions where the same actions make progress. This new action-based sensor functions under the limitations of our physical sensors. If that's the case, then the current collection of action-based sensors is incomplete. There are action-based sensors that currently cannot be found, and these sensors derive from plans other than those found through backchaining. Our question is clear. How can we find all possible action-based sensors that can be used to solve a problem? To find these missing sensors, we start with a plan. While a robot may be able to take many actions at different points of a plan's execution, we want only those that get us closer to the goal to be part of our action-based sensor. This is defined with a progress measure, which is a function on the states of the world based on the order in which a robot visits them. As the robot moves closer to the goal, it transitions from high-valued states to low-valued states. In our backchained example, the progress measure is simple. Even for these other plans, the progress measure is easily defined. These plans give action-based sensors. Non-determinism complicates the issue. What if our robot non-deterministically selects one of these two paths at the start of execution? Once chosen, the robot is committed to its path, but we cannot know ahead of time which it will choose. When both paths are options, the issue becomes obvious. The robot, depending on the path, visits the same states in different orders. When we consider the two plans simultaneously, a progress measure fails to exist. Actions that are progress making for one path may lead to backwards progress in another. We call these unsatisfiable constraints crossovers, as they occur when different paths in a plan cross over each other. This can occur when different choices made by the robot result in conflicting orderings, or when a robot revisits the same state multiple times. In short, plans have progress measures define action-based sensors are useful and we want to define all of them. However, some plans have crossovers. These crossovers break progress measures, and no progress measure means no action-based sensor. If we want to find all action-based sensors, we have to first resolve all of the crossovers to obtain a progress measure. So how can we do that? If we were to take a plan and place it onto the world, tracing the path the robot takes, then crossovers would be tangled paths that loop over themselves. The simplest way to resolve such an issue is to clip away parts of that path, removing actions that would allow a robot to backtrack. To enumerate all of the crossovers, we must first build this relation between our plan of interest and the world on which it operates. For this, we have developed an algorithm which we call CLIP. CLIP consists of 3 stages. It first builds associations, then it finds crossovers, and finally it removes them. Relating the plan to the world effectively strips it of its own structure. Our robot can no longer make a non-deterministic choice at the start of execution and be bound to that, as at each state in the world, the actions of both paths are now available. This is the motivation behind our plan-world interaction graph, or iGraph, which maps states in the plan to states in the world to create a new plan. In this new plan, crossovers are easy to discover. Where before these cycles were implicitly defined through an ordering of states, they are now explicit as cycles within the graph itself. The edges in these cycles become our candidate edges for removal to resolve the crossovers. For each cycle in our new plan, we must find a way to resolve it. For each crossover, CLIP tries removing various configurations of candidate edges while still maintaining the plan as a solution to the planning problem. CLIP's output is plans which have resolved all crossovers. Because we have collapsed any structure from the original plan when creating the iGraph, the output of CLIP mixes and matches edges from the input plan. Our original plan of 2 paths yields 5 output plans, as shown here, each of which combines pieces of both of the original plans. Now that we have plans for which we can make progress measures, we can transform them into action-based sensors. Each state in the plan has an associated value with the progress measure, and with it we can determine what actions in the plan take us to lower valued states. These are the actions we would like our action-based sensor to give us. We can create a partition on the world based on which actions make progress in which regions. These partitions define action-based sensors. Regions that have different actions to progress under them must be distinguishable such that the agent can always make progress towards the goal. By finding all possible ways to resolve crossovers through CLIP, we are now able to define all action-based sensors which can be derived from the original plan. Now, when it comes to the process itself, the resolution of crossovers by CLIP is a significant choke point in obtaining all action-based sensors. Although we only consider certain candidate edges for removal from the plan, the number of potential outputs is quite large. For a given crossover of size n, there are 2 to the n-1 ways to resolve it. While this set can be slightly reduced by disqualifying some edges, the existence of multiple crossovers means the search space quickly grows very large. We can step around this issue by having CLIP only return some solutions, or by returning early to give a partial solution that may still have some crossovers. However, it is difficult to determine ahead of time if one way of resolving a crossover is preferable over another, or if that choice will impact our ability to resolve other crossovers that CLIP has not yet treated. To obtain the full family of action-based sensors efficiently will require further work. In terms of follow-up work, there are several interesting avenues to explore. Making progress is a rather general term, and one could easily conceive of a problem where the progress measure is applied to sets of states, and obtaining a more precise state estimation is part of the process to solving the problem. Up to this point, we have also assumed that a single state in the plan corresponds to at most one state in the world. There exist plans where this is not true, and one state in the plan may correspond to multiple states in the world, complicating the question of how we associate the plan to the world itself. Some problems also simply cannot be solved purely with good sensors. Agents must make use of internal state, which changes how we can interpret seeing the same sensor readings at different times. We're very interested in pursuing this close association between how a robot makes use of state and how that affects its sensing requirements. That's all, and thank you very much for your time.